Good afternoon, everybody. Gives me great pleasure to introduce Peter Chubb from Data 621.
Hi, folks. Normally when I'm in front of an LCA crowd, I'm talking about something to do with work, that's to do with scalability or Linux kernel or something like that. Today's different. All that I'm doing today is hobby stuff. It's got nothing whatsoever to do with work, and I didn't use any work time in preparing these slides. It's also got nothing whatsoever to do with Linux. This is me scratching an itch that I had. And it's sort of way out there. But anyway, I had great fun doing this, and I'm hoping you'll have some of the fun as we go through. This all started because today, if you get your components, they look like that. They're sort of tiny things that you can't see without a magnifying glass. And unless you know which reel you took it from or which envelope you took it from, you've got no idea what they are. Those could be resistors or inductors or capacitors or maybe even a diode. They happen to be inductors, but you can't tell. When I grew up, electronics looked like this. These are actually, Ducon was in Melbourne making capacitors. STC, who made the Made in Australia electrolytic there, was also Australian. Why can't we keep making components in Australia? In your backyard. And these capacitors, these resistors rather, they're carbon film. They work great at high frequencies, but nobody uses carbon film capacitors much anymore. Everybody's gone to metal oxide, which are not as good in some ways. Anyway, that's where I come from. I've still got this radio. It still works, except that some of the capacitors still need fixing. Let's start with resistors. What a resistor is something which impedes the flow of current and converts a current to a voltage that's proportional to the current. So you can think of it as a current to voltage converter. And it works essentially by constricting the flow. The longer the resistor thing, the higher the resistance and the more flow it restricts and the higher the voltage across it. The bigger in cross-section it is, the easier it is for the current to get through, and so the lower the resistance. So you have resistance is proportional to length divided by area, and you measure it in ohms or volts per amp. 1 ohm is 1 volt per amp, and it's really just a poor conductor. Where in your house do you have a relatively poor conductor? Yes, in your heater, but I don't want to use wire, and I don't want to have to pull apart things that I don't have to pull apart and might get in trouble from my partner if I pull them apart and they don't work again afterwards. So not the kettle, no. And not yourself? And not yourself, no. But that's a good answer, though. It's just that I don't really want to wire you into my radio. I pulled the lead out of an HB pencil. You know, you can just slice it along the length with a scalpel and pull the lead out. And then you can put a couple of wires on it, glue them to make sure they stay there, and measure it. And this one's about 10 ohms. Looks pretty good. It's very, very stable. I increased the frequency at which I measured up to about 500 kilohertz, which was the limit of my measuring equipment, and it didn't change much. I heated it up with a heat gun, and it didn't change much. Really good resistor. How do you measure how good a resistor is? Well, if you've got a resistor, it shouldn't change much if you wiggle the ends, if you've got a bit of vibration, if you sort of kick it or drop it. It shouldn't change much if the temperature goes up or if the frequency goes up. And it shouldn't change much if you put a high voltage across it or a low voltage across it. It shouldn't be voltage dependent unless you want a voltage dependent resistor. And it shouldn't be noisy except for the unavoidable thermal noise. Now, anytime you've got an impedance in your circuit, you're going to have noise in proportional to the square root of the temperature times the resistance times the bandwidth over which you're measuring. And that's why, if you've got a radio telescope, you put your preamp right there, you run it at a low impedance, typically 50 ohms, or even less, and you cool it with liquid nitrogen to try and keep the thing low noise, and you use a very restricted bandwidth that you're looking at. I want to produce general purpose ones, so it doesn't matter so much, but you only want the thermal noise. I've had resistors that when you put them in a circuit, the front end of the circuit, they go because there's something wrong with that resistor. This resistor, I couldn't detect any noise with the instruments I had. But vibration and movement, when I went back the next day, my resistor looked like this. We obviously need something better. So, let me just do a quick side into why I would expect frequency to affect resistance. Anytime you've got an electron moving, It generates a magnetic field around itself. So if you've got lots of electrons moving down a wire or down a resistor, you're going to have a magnetic field associated with that. Anytime you move an electron in a magnetic field, it experiences a force that's perpendicular to its direction of motion. The force is proportional to the speed at which the electron's moving. So if you're moving fast, it's going to be zipping out quite hard. If you're moving really slowly, it's not. If you increase the current to a few thousand amps, then the electrons start moving quite fast and start moving to the edge. I don't have a few thousand amps to play with. So the alternate way to do it is just to increase the frequency of the AC, and the electrons are sort of jiggling backwards and forwards faster and faster and faster. When you do that, they all move to the edge. This reduces the effective cross-section of your resistor and so increases the resistance. And it happens depending on how much magnetic field you get, and that depends on the substance. Let's have a look at a few of them. This is the 63% point. 63% of the current moves in the outer 1.4 millimeters for graphite at 1 megahertz. Or for iron, which is actually a magnetic material, only 7 microns, which is why you never use an iron core, an iron resistance at high frequencies. It just doesn't work. It's also why, if you look at the great big long transmission towers, they consist of a steel core that no current goes through and an aluminium outside, because they're designed so that the depth of the aluminium is the skin effect at 50 hertz. And so that's how you get low stuff. It's also why, if you look at your normal resistor, they're sort of cylindrical. Or they're really thin film construction in the SMT resistors, so that you don't have much skin effect and you can use them at high frequencies. It's also why, if you've got headphones on, that stuff's got Litz wire in it. Litz wire is wire that's lots of very, very fine strands, all individually insulated from each other. So you get the skin effect for each strand, and overall, you get a bigger cross-section than you would if you had just one wire of the same thickness. And so the manufacturers can put less copper in that wire. It also makes it a real pain to solder when you want to put a new plug on. And it's also why carbon resistors in the past were really popular, because the skin depth is really big. So let's try and make a thin film resistor. What we need is some kind of applicator to make a thin film of carbon. Pencil. You really want a 2B or softer pencil. HB, it's got too much clay or polymer in the lead and it doesn't actually conduct very well at all. But what I did was I took a piece of card. My original one was just a card from a shirt box. Cut 4 holes in it, put wire through, crimped it flat, and then drew until I had a resistor. This one was about 20K. And it seemed to have reasonable properties except for vibration. Every time you wiggled the wires, the resistance would change. We need a better way to attach wires to graphite or other substances. It's really mechanically unstable. So what are we going to do? Well, I've tried mechanical, it shakes loose. Solder only really works between copper and things that are compatible with copper. Graphite isn't a metal. And if you want to solder copper to aluminium, you need to use special solder and special flux, and it's a world of pain. So we're left with glue. And the problem with glue is that most glue is an insulator, and it's going to get in between your conductor and your graphite. So we need a conductive glue. Now, you could cheat and go out and buy some on eBay, but I want to do everything from things I can find around my house. So I go and find, in my kid's craft box, some PVA glue, some pencils, and a mortar and pestle out of the kitchen, right? And you take the leads out of the pencils and bang with the mortar and pestle till you've got nice fine graphite, and then mix it all together, and Bob's your uncle. This turned out to be a really bad idea. It was hard work, and cleaning the thing up, ready to make the garam masala for dinner, was a real pain. And took about, after 10 minutes of grinding, it took about 3 hours to get the thing clean enough that I could use it for food again. So I happen to have some graphite lubricant in the garage for doing hinges and locks around the house. This Pressol stuff. You can buy it in Bunnings or you used to be able to buy it in Kmart, but Kmart's gone downhill. Mix that with your PVA calf glue about half and half. Test it to find out how conductive it is. If it's not conductive enough, add some more graphite. If it's not sticky enough, add some more glue. Stir it all up really, really, really well, and then use it within just a couple of weeks. What I found was that after a couple of weeks, it stopped being quite as conductive. It was still a bit conductive, but it became less conductive and a lot less sticky. So you just mix up as much as you need and then use it. You can use this as a resistive paint. The problem is that it's really hard to get the value of resistance you want if you just paint between the two conductors. It's really hit and miss, and there's no way to trim it afterwards easily. I suppose you could hit it with a scalpel or something, but yeah. And the other thing to watch out is because it's PVA glue, it dissolves in liquid. So over time, if you want to make an electrolytic capacitor, which I'll talk about later, if you use this glue, it will eventually dissolve. And the third thing is that I didn't discover this until I've made 3 more resistors, which didn't work. When the glue is set, the actual surface, the outer surface, is non-conductive. So you have to set up so that everything's conductive beforehand and then put the glue on. So, next resistor. I did one where I glued the wires onto the card first, and that didn't work. So this is actually the 4th resistor. But anyway, you draw 2 graphite circles, tape some wire on, hint for the newcomer, strip both ends of that wire. If you try and strip it afterwards, it'll pull it off. Glue it on, and then start drawing with your pencil. This particular one ended up about 33K, which is what I was aiming for, which was good. You have to keep drawing until the resistance is just over what you want, and then wait for about half to 3/4 of an hour, because the resistance will keep dropping after you stop drawing. What's happening is the graphite, after you've finished drawing, actually settles and bonds to itself a little bit, and so decreases the resistance. If you go too low, just use your pencil eraser and make it back up again. Right? I also made one at 1 megohm, which I unfortunately got destroyed before I managed to take a photograph. At the 9 volts that my multimeter works, it was reading 1 megohm. But I have a mega, which is an insulation tester that measures resistance at very high voltage. At 500 volts, the resistance drops to 800K. At 1,000 volt, it dropped to 300K. What's going on? I want my resistors to be good, whatever voltage I use. My guess is it's to do with humidity and conduction over the top of the graphite and through the card. I tried to make a thing with just card and the graphite blobs without anything through, but it didn't show any resistance at all. So I might be wrong here. But I did notice that if I breathed on the resistor, the resistance would go down. So, next try. I grabbed some rideable tape, this stuff. You know, ordinary sticky tape like you use for your stationery. You can get a version that you can draw on with pencil, and it works. There's a number of manufacturers. Scotch make one, Officeworks makes one, there's lots of them. And this one, after I'd put it on there and put another layer on top afterwards, it didn't change resistance when I checked it with the Mega. Success. And there's a 200K resistor, which was enough to check with the Mega, and it worked. And I did some other ones as well, and they're all nice. So up here afterwards, if you want to come and have a look, there's some with tape and some not on tape. If the resistance is low enough, it doesn't matter. If it's less than about 50K, you're not going to be putting 1,000 volts across it anyway. But for anything that's like 200K or up, you probably want to use the tape trick. And you probably want to use the tape anyway to stop the graphite getting rubbed off and changing your resistance over time. But anyway, that's resistors. I could heat it up, didn't do much. I didn't heat it above 90 degrees because it would start melting the plastic. And it was still within 5%, which is the limit of my measurement capability anyway, at about 500 kilohertz. So, success? So it's possible to make really good resistors. And voltage-independent ones, and ones that are almost frequency independent to the limits of my ability to measure them, and that they have reasonably good temperature response. I didn't measure noise. Okay, that's resistors. Let's try capacitors. A capacitor is a gadget that stores energy in an electric field. It consists of two pieces of metal, which we call plates, separated by an insulator, which we call a dielectric. The idea is that on one side, you take electrons away, and the other side, you put electrons on, and that causes an electric field between the two plates. In your dielectric, you can think of lots of atoms that are roughly spherical on the surface of the dielectric. When you put an electric field there, that electric cloud of electrons deforms, so it gets sucked towards the positive terminal and pushed away from the negative terminal. Depending on the material you've got there, it's harder or easier to deform that electron cloud. So you end up with a dielectric constant that depends on the dielectric material that controls how good your capacitor is. The amount of capacitance you have, therefore, is proportional to the overlapping area, inversely proportional to the distance between the plates, and proportional to the dielectric constant of the substance you've got in there. You measure a capacitor in coulombs per volt, where a coulomb is 6 times 10 to the 23rd something electrons, or thereabouts. I forget it. It's Faraday's constant, and I can never remember exactly what it is. But a farad, which is 1 coulomb per volt, is a huge capacitance. You only find those in supercapacitors. Most of the ones you need for radio are measured in picofarads or nanofarads, and occasionally microfarads. So, capacitor dielectrics. I showed you some wax paper capacitors earlier. They were one of the earliest ones to use because they're dead cheap to make. They're still used for very high voltage capacitors. If you're making a capacitor to work with, say, 500 kilovolts in your power station, you tend to use aluminium foil and paper and put the whole thing in a big tub and pump oil through it to keep it cool. Wax paper has the problem that over time, like 20 years or so, moisture gets in and displaces some of the wax and causes a short between the plates. And at that point, the capacitor goes bad and becomes leaky. What's more, those leaks tend to be voltage dependent. So you can have a capacitor that measures perfectly well on your capacitance meter, and you can't see any leakage at 10 volts or so, or whatever the working voltage is. But at a kilovolt, you start getting leakage. So that's wax paper capacitors. There have been lots of different plastics used for capacitors. You can make plastic capacitors up to about 600 volts. Polystyrene capacitors have very good high-frequency characteristics, so they tend to be used in high-frequency radio stuff. Polyethylene capacitors, they're the old green caps. They're just general purpose, you name it. They tend to be a little bit more lossy than some of the other sorts, but in most cases that doesn't matter. Ceramics and glass, the very earliest capacitors made were glass jars. They were just tall glass jars with a layer of aluminium foil on the outside and on the inside. You may have seen these attached to Wilmshurst generators in the museum. They only had, a few tens of picofarad of capacitance, but they could stand tens of thousands of volts. And they used to call them Leyden jars after the engineer who invented them. Mica is often used for high-frequency capacitors. You take a very, very thin slab of mica and silver both sides. They work really well at high frequencies, but you can't use them in blocking applications where you want to have a constant voltage across them, because over time, the constant voltage makes the silver migrate through micro cracks in the mica, and at that point they die. And there are other more exotic things. Air for variable capacitors, depleted semiconductor for reverse biased diodes, for voltage-dependent diodes. I'm just going to try and make a wax paper capacitor. So, this is what you need. You can find all of this in your kitchen. Some greaseproof paper, a piece of aluminium foil, and a candle. Take the candle out of its aluminium container and then use it like a crayon over your wax paper. Rub it all over the place, on both sides, make it really, really covered. Then layer a sheet of aluminium foil either side of the wax paper. Put another bit of greaseproof either side to protect your iron and iron it on a low dry iron. And that will compress it and melt the wax so the aluminium sticks to the wax and the greaseproof. I did this, and I end up with this 50 picofarad capacitor. As you can see, it's about 21 centimeters a side. It's 50 picofarads for 400 odd square centimeters, and it had no leakage that I could detect at 1,000 volts. Nice capacitor. It's not a particularly convenient form factor. That's this one. Can you imagine soldering that into your circuit? How do you know whether you've got a good capacitor? Well, this side's the negative, right? If you've got a good capacitor, it shouldn't be affected by temperature. If you heat things up, it shouldn't affect anything. It shouldn't be affected by voltage up to the limit of the dielectric strength that you've got there. It shouldn't be affected by frequency. Some capacitors have some degree of inductance associated with the wires and the way that the current gets distributed over the plates. They're no good for high frequency. But for a good capacitor, it won't be affected by that. If you jiggle the wires or otherwise vibrate the thing, it shouldn't be affected by that. And humidity shouldn't affect it in the short term. Over long term, I don't care, 20 years. And it should have a low equivalent series resistance. That is, all of the effect of the capacitor should be because of the capacitor, not because of resistance in the plates or in the wires leading to the plates. It should have low inductance, so it acts like a capacitor, not like a coil. It shouldn't leak current through the dielectric. It shouldn't have any losses there. For some dielectrics, particularly some plastics, the act of charging it up and discharging it, deforming those electron clouds I mentioned, that dissipates energy in the dielectric, and so it heats up. And you want a dielectric that doesn't do that. And it should have a high dielectric strength, which is basically the same as saying it doesn't go with resistance, with voltage. All of those are good. The thing that this capacitor did was temperature. Remember those really hot days we had just before Christmas? That's what happened to my capacitor. It just delaminated. And now instead of a 50 picofarad capacitor, I've got a 20 picofarad capacitor, which is not what I wanted. So I've obviously got to do something better. So I thought, okay, if I can't do a wax paper capacitor that lasts, maybe I can do a plastic capacitor. So I pinched some book covering plastic, the type you use for kids' school books, and some more aluminium foil. And I had some sticky aluminium tape. My girls weren't very happy, but I pinched it from the craft box. And then what you do is you take yourself a piece of the tape, the book covering plastic. This particular one is 80 micron thick PVC. Sorry, no, polypropylene. Stick it on the al foil, stick the sticky aluminium foil on the other side, this stuff, and then measure it. This one, 820 picofarads for only 65 square centimeters. That's much, much better, isn't it? And it still had no appreciable leakage at 1,000 volts, and I couldn't affect it by temperature, which was lovely. And I made this one back in July. 6 weeks later, I measured it again. It was only 240 picofarads. And then I measured it last night, and it was like 100 picofarads. Something's going wrong with my capacitor. My guess, and I don't know this yet, is that some of the capacitance that I measured when I first measured it was from the dielectric in the glue, not in the plastic. And as the glue settles and dries up over time, the capacitance changes. That's my guess. I don't know for sure. So what I need to try next is try different glues and maybe get some I've got some archival book covering plastic that I use from my books that's not sticky at all. And I could probably use some sticky craft glue, the spray stuff, and glue some aluminium foil onto that and try it out and see what happens. But right now, I don't know. So how can we make bigger caps yet? These ones like the couple of nanofarad at the most. I did try a different book covering plastic, by the way. This one here, which is about the same size as that one, is 1.5 nanofarads at the moment. I haven't had it long enough to find out whether it's going to decrease over time. It's a different book covering plastic. So what we can do is we can try increasing the area or decreasing the distance between the plates. So what I'm going to do is make an electrolytic capacitor. What we're going to do is we're going to take some alfoil, etch it a little bit to increase its surface area, and then grow an oxide or carbonate layer on the aluminium. And we're going to grow it just as thick as is necessary to prevent a reverse voltage through. And we'll use an ionic fluid as the other electrolyte. You can do this at your home. This maximizes the area and minimizes the distance between the plates because it's just the thickness of that oxide layer. What you need is some demineralized water, the kind you use to fill up your steam iron, and either some borax or some bicarbonate soda, both of which you've probably got floating around the house already. If you use borax, you need to heat up the demineralized water before you start dissolving it because it doesn't dissolve in cold water. Bicarb is fine. Both work just as well. So what I did was I took a carbon rod, and I'll tell you how to get a carbon rod a bit later, wrapped a bit of wire around it and glued it with some other wire glue. I took some aluminium foil and put it into a jar, filled up the jar with the bicarb solution, or the borax solution, I've tried both, wrap the carbon rod in a scrap of cloth to stop it from touching the aluminium, and dip it in. And then attach this to my regulated power supply. Set the power supply to 100 milliamps at whatever, 30 volts, whatever, and run it in reverse for a little while. Eventually, you're going to have the aluminium as an anode and the carbon rod as a cathode. But for now, you're going to swap those round and run it in reverse. And that will etch the aluminium and make it sort of not shiny anymore because it's pitted with lots of little tiny things. And if you pull it out, you'll see that. So when you've done that for 100 milliamps, then you put it the other way, set it to 500 milliamps this time, and 30 volts. And what you'll see is that the actual voltage will start off about 3 volts and gradually creep up while the current's sitting on a 500 milliamps until it gets to 30 volts. And then the current drops until it stabilizes. In my case, it stabilized at about 50 milliamps. And when I measured it, which I did by hooking into a 555 timer circuit and measuring the pulse rate, at about 400 microfarads. It is quite leaky. But if I did a lot of charge and discharge cycles, that leakage current dropped to about 2.5 milliamps, which I think is pretty good for a homemade capacitor. There's a few things that went wrong. Tap water doesn't work. I've been told by a friend of mine, William Holstrom, that if you make your solution, then leave it for a couple of days before adding any aluminium, it does work, but I wasn't able to try that. I did try leaving it to form overnight, and just nothing happened. It was still running at 500 milliamps in the morning. Hang on, what am I doing here? Too many buttons. Lots of gas gets emitted while you're doing this, so you need to do it in a well-ventilated area because you're essentially electrolyzing the water while you're forming the capacitor. That's one of the reasons, by the way, that if you put a capacitor in reverse, an electrolytic capacitor in reverse, it eventually goes bang because you're electrolyzing the liquid that's inside the capacitor and generating hydrogen and oxygen, so don't do that. If you accidentally drop a bit of the wire glue onto the alfoil and that gets into your electrolyte, you've got a dead short and nothing's ever going to happen. And that wasted me 2 days. If you leave it overnight, it dries up a little bit, especially in these hot weathers. And so your capacitance decreases. When you top it up again with more demineralized water, you need to reform that bit of the capacitor that you've just put in there. Theoretically, you wouldn't need to do that. And for short term, you probably don't, because you can pull the capacitance, you can pull the aluminium foil out, and it reduces the capacitance, you can put it back in, and it increases it again, which, by the way, gives me a really good idea for a variable capacitor. Typically, if you make an air core, typically your commercial variable capacitors go up to maybe 500 picofarads. With something like this, if you've got a scrap of aluminium dipped into an electrolyte, you could probably make it about, 500 microfarad variable capacitor. But I haven't done that yet. Anyway, so summarizing capacitors. It's possible to make good ones, but long-term stability seems to be an issue that I need to investigate some more. I want to try some more different dielectrics, and I want to work out a better way of packaging these things, perhaps rolling them all up and tying them up with a bit of string. Then we could have brown paper packages tied up with string. But let's go on and talk about diodes. If you want a diode, you need a semiconductor. These are the common semiconductors that you've all heard of, germanium, silicon, gallium arsenide. I don't have any of those. You can buy chunks of silicon and chunks of germanium in rock shops sometimes. They're left over from the semiconductor industry. I haven't seen any in Sydney, but I have seen some in the US. I'm not going to do that because I'm still trying to do stuff that you can find around the house. But there's some other things that you can do. Metal oxide. It used to be that before the days of germanium and silicon semiconductors everywhere, you'd find these things that looked like stacks of coins inside your radios, which were selenium carbide rectifiers. Hang on, what have I done here? I've gone too far. Yeah, here we go. So what I'm going to do is I'm going to try metal oxide and use copper and cuprous oxide semiconductor. And I'm also going to try using zinc oxide a little bit later on. But let's talk first about where you can get copper and zinc. Well, for copper, let's have some old 1 and 2 cent coins. They're 97% copper, that should be enough, eh? And for zinc, you can get very pure zinc by pulling a battery apart. And we'll come to that in a little while. What you need to do is clean those coins really, really thoroughly. I use the aluminium and bicarb trick. If you're not aware of this, what you do is you take a container, put some aluminium foil in the bottom of it, put your coins in so that they actually touch the aluminium. Ideally, they don't touch each other. They're too overlapping there. And then add some bicarb solution that you've made saturated. In just a few minutes, you'll see the coins start to change color and become nice and shiny again. Pull them out, rinse them off, rub them with a soft cloth, and you've got really shiny, clean coins. And it's almost no effort. If you don't do that, you've got to sort of rub them with steel wool, and it takes forever. So clean the coins thoroughly, and then heat them up. I use my barbecue burner. So I put them on there, turned it up, and waited for it to turn first black, and then salmon pink. And you can see around here, it's black in the middle, that's copper oxide, and it's just going salmon pink around the edges, that's cuprous oxide. It's the cuprous oxide that you want, not the copper oxide, because copper oxide is just boring black stuff. It's the cuprous oxide that is the semiconductor. So then, I have to try and probe that for diode capability. How do you probe it? Well, the easiest way is to use a curve tracer. If you go out and buy a curve tracer, it'll cost you, well, second-hand, maybe 600 US. New, thousands of dollars. So let's make one out of a transformer resistor and a cathode ray oscilloscope that I already have. What you do is you've got a transformer there so that you're not referencing your AC to earth at all. And you put your Y across a 1K resistor, which you can make, and your X from the other side. If you're using a 1K resistor, you have 1 volt per milliamp through the whole circuit. And your unknown goes where the rectangle is. You can use a signal generator plus a balun, but I was too lazy to wind a balun, so I used a filament transformer which gives you 6.3 volts connected to a variac so I could adjust the voltage up and down. What does this look like when you look at the traces? Well, if you have a complete open circuit, you have volts going horizontally up to, in this case, 1, 2, 3. I said it's a 6 volts peak to peak on the variac. If you have a short circuit, you just get a vertical line. In this case, 6 milliamps peak to peak. If you put in a 1K resistor, you get a 45-degree line. If you put in a higher resistance, you'll get a lower line, a lower slope. If you put in a capacitor, where the current and the voltage are going to be 90 degrees out of phase, you'll get something closely approximating a circle. And if you put in a diode, come on, where's my diode? You'll get something that looks like this. It might not be up that way, it might go down. But the diode's reverse biased here and forward biased there. That's a silicon diode, so the forward current is about 0.6 volts. All right? So, what about my copper oxide thing? Well, I probed, and I probed, and I probed, and I probed for about 3/4 of an hour, and eventually ended up with this curve. Now that looks like, sort of like a diode. We've got a forward bias bit there, but the reverse bias bit looks more like a resistor. So it looks like we've got an equivalent circuit that looks something like that. At this point, I was getting bored with copper oxide things, so I decided to move on to zinc oxide. Because this one was leaky, it was really fiddly, and I could never find the spot twice where I could see that diode action. So I was really glad I photographed it when I did. So what can we do to fix that? Well, I want to try finding some purer copper. If you read the early radio mags, they talk about Chilean copper being superior to any other sort of copper for copper oxide stuff. And the reason for that is the trace elements in the Chilean copper as opposed to the stuff you get from Cornwall or Australia. So it's obvious that different copper sources have different properties. So I want to explore that. H.B. Friedrichs on his website has a trick for creating a more uniform cuprous oxide layer. He alternately dips his copper into hydrochloric acid, which you can just buy for cleaning brickwork, and a borax solution. And the borax reduces some of the copper oxide into cuprous oxide. And so you end up with a nice thing. So that website, it's a really good website for looking at copper oxide rectifiers and things. The other thing you can is that some people report that the cuprous oxide is light sensitive. And you can actually get a small voltage if you shine a bright enough light onto the cuprous oxide junction. You can also see that the diode behavior changes a little bit with light. So it could be that we can make a light-dependent diode here. And that could make an interesting project later on. But that's all to try later. In the meantime, I want to look at zinc. So where are we going to get our zinc? We're going to pull a battery apart. This is from Wikimedia Commons, good place. If you take a normal zinc-carbon cell, this is the heavy-duty one, not the alkaline one. It's got a really pure zinc casing on the outside. It's got, on the inside, a mixture of manganese dioxide and black carbon. And right in the middle, it's got a carbon rod to act as your anode. And then between the manganese dioxide and the zinc casing, there's some absorbent paper soaked in ammonium chloride. All of those substances are almost harmless. People used to drink sal ammoniac as a headache remedy. And they used to use it in dry form as smelling salts. It's almost harmless. So that's what an ideal thing is. Don't use an alkaline battery. If you use an alkaline battery, the ammonium chloride, which is almost harmless, is replaced by a caustic hydroxide, either potassium or sodium hydroxide, which will give you nasty burns if you pull the battery apart. So don't do that. But the heavy-duty ones, fine. When I did that, I took my battery and pulled it apart. You end up with a piece of tin plate, which is really useful stuff, the pure zinc casing, I've got it here, and you can see a plastic cap on the top. Pull the plastic cap off. It's really easy to do. Just leave it off with a pair of pliers. And you end up with something that looks like this if you look on from the top. There's all this black gunk around the outside. That's manganese dioxide mixed with black carbon. Scoop that all out and throw it away. Keep the carbon rod. You can see the paper here. Throw that away too. You don't need it. And just wash the zinc outside thoroughly. Then cut yourself a piece of the zinc and a piece of the tin plate. Use the tin plate as a baking tray. Put the zinc on top of it. Stick that on your barbecue and heat it up. As it heats up, it'll melt. It melts at a fairly low temperature. And after it's melted, it'll start changing color. And it'll get to a sort of bright greeny yellow color. That's when you stop. You hold it there for 30 seconds or so and then turn it off and let it cool. If you're lucky, the zinc will have bonded onto the tin plate. That's good because you can solder a wire onto the tin plate and have a good connection. If you're unlucky, you're going to have to use wire glue to glue the thing on, because if you heat the zinc up again, you'll destroy the oxide again. So don't do that. So there's your thing. Then you just probe around. You need a different conductor to touch with. I wanted to try and find something which is a bit more mechanically stable than I had before. So I took a clothes peg here, drilled a hole through it, put a screw in, put a bit of lead on the end of the screw and melted it on, a bit of solder, and then clipped it onto the zinc. Turns out that zinc oxide is rather fragile. This went straight through and I had a dead short. Not very helpful. So what I did was use the same screw, attached a bit of wire here and a bit of graphite, and I ended up with something that looked like this. This is reversed from the ones we had before. So here's your forward zone with about 2 volts forward voltage, and here you've got your reverse zone, and it's starting to show some Zener effect at about 4 volts. Yeah, okay. That's good enough for an envelope detector for an AM radio. So let's build ourselves a crystal set. This is going backwards. Where am I going? So here it is. This was working. I built it with my daughter about 3 years ago. She took it to school, and I didn't see it for 6 weeks. And what she reported, though, was it didn't work after 2 days. What I know now is that that capacitor probably went low value, and so instead of tuning the broadcast band, it gradually got to the 160 meter band, then the 500 meter bands, then the very, very low frequency band where there isn't any activity. So what I've got to do now is work on better mechanical packaging, other copper sources, explore zinc oxide negative resistance, which I didn't get around to talking about today, unfortunately. Try some carbon microphones. The early prisoner of war built microphones for their radio transmitters, their clandestine radio transmitters, out of the carbon rods out of batteries and razor blades. And if you can make the razor blades balance the carbon rod correctly and put a paper cone on it, you can get a crude microphone. You can also, by arranging the razor blades and carbon rod in a different way, develop a detector. And I want to explore and play with that. They called those ones coherers. I want to try making light bulbs. You know that first resistor I made? I tried making one out of the much thinner lead that you get from one of the propelling pencils, you know, the 0.5 millimeter ones. When I started putting an amp through, it started glowing white hot and melted and sort of puffed up in smoke. I think that if I take a jar with several of those inside and pass a couple of amps through one of them, the first one will do that, and then after that there won't be any oxygen inside. So the second one will just glow. Right? So I want to try that. I want to try other glues. When I'm doing bookbinding, you can use egg white mixed with water as a glue, and it's very, very effective. So I want to try that instead of the PVA glue. I also want to try silicone sealer. Now, you know silicone sealer, when it dries, it's all sort of rubbery. I figure that if we have silicone sealer mixed with graphite, we might get a touch-sensitive glue. And a friend of mine tried this, and he says it does. And so you can make yourself a touch panel. I haven't done this, but my friend did, William Hallstrom again. You mix your silicone sealer with the graphite, spread it over a bit of card, nice and thin, embed wires on either side, and then, depending on where you touch it, you'll get different resistances between the wires. And so you can have a crude touchpad made out of stuff you can find at home. Try shellac. Shellac mixed with methylated spirit. Eventually the methylated spirit dries and the shellac sets, and you end up with a nice glue. We could use that mixed with graphite. I don't know whether that's going to work or not. Anyway. Yeah, doesn't matter. You're not going to eat it. You can make components, and you can even make reasonably high quality ones, but it's really fiddly. And they might not work tomorrow. But I had fun. Why not have a go? There's lots more to explore. So I hope you go home, look in your kitchen drawer, find some stuff, and build some components, and let me know what happens. Okay, questions? Yep, up the back there. Run with that microphone, sir.
When you said look for sources of carbon, I immediately thought, have you considered a burnt toast resistor?
Yeah, you can make burnt toast resistors. In fact, you can, with a, if you press your toast, you get different patterns on it, and you can actually make a toast circuit.
A quick comment on ammonium chloride. It's actually used in candies in the Scandinavian countries.
Yes.
The most popular flavor, so it's very harmless.
Yeah.
Just don't lick it directly from the battery.
Yeah. I know you can use it to provide an ammonia flavor, and yeah. Any more questions, comments? Irving? Oh no, there's one over there first. Alex.
Seeing the oscilloscope made me think, can you make some sort of phosphorescent screen?
Yes, you can. If you look at Niall Steiner's website, you can see how he did it. But you need a vacuum pump of some sort. But you need to be able to evacuate a tube. But you can make an electron gun, and you can make yourself a little cathode ray tube without too much hassle. It's easier to make one that uses magnetic deflection than one that uses electric deflection. So more like a television tube than a oscilloscope tube. But yeah, people have done it. Any more? Irving had a question and then...
I'm afraid we're out of time.
Aw.
But Peter was saying earlier he's more than welcome for people to come and
Yeah.
have a look at everything he's made, and I'm sure he'll be happy to answer your questions then. So if we could just thank Peter for his very creative talk.
Yeah. There's also, I didn't go through, we ran out of time, but you can make negative resistance elements. And if you bias your zinc oxide plus a thing at the right time, you can bias your operating point to here and actually get a gain element and build oscillators and regenerative receivers and amplifiers. But I didn't get time to talk about that. Anyway.
And also, just as a small gesture of thanks, I'd just like to present you this one here from
Thank you, sir.
LCA.
Ooh, nice.
Just another thanks for Peter thing.